Okay, we've learned through our study of Maclaurin series the amazing fact that the cosine of x can be represented with a Maclaurin series or a Taylor series centered at x equal to 0 with even powers of x as follows. It's a 4 plus dot, dot, dot. Those are dots. The nth term then, 2n, factorial. And amazingly, the left-hand side of the equal sign equals the right-hand side if you go out for an infinite sum. Now, in reality, we will never be summing up an infinite number of terms on the right-hand side of this equation. We will be truncating this or cutting it off somewhere. When we do that, we now are getting some kind of an approximation. So we might say if we wanted to approximate the cosine of x, we would say it's approximately equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And that's only approximate. And then we wonder, well, how good is that approximation? Notice we have names for these approximations. We would call this the Taylor polynomial of order 4 for the cosine of x centered at x equal to 0. Now, your homework, when we approximate the cosine, we're going to study what is the error. What is the error in this term? And for our first homework question, we use your calculator to find what? The interval x such that the error, or the absolute value of the error, x, which would be equal to what? Well, equal to be the cosine function, that is the function we're trying to represent, minus this polynomial up here. I'll just write it like this. If you plot this in your calculator, you will find that, I need a time thing, like con here. If you plot this in your calculator, you will find a bowl-shaped function where the error term looks like this. And if we set up, we were looking for the interval such that what? The error is less than 0.002. Okay? So if you put this in your calculator, let's see if I can switch pens here. And this is y equals 0.002. You want to find out where do these things intersect. Where's this and where's that? And when you do this, you have to set your y window small, right? Set your y window small, and you find the answer is, this is 1.066, sorry, 1.066. And you notice this is an even function. Cosine's an even. These terms are even. So it's even about the y-axis, so minus 1.006. Okay. Now, what if we did this, the entire thing, instead of using our calculator, we use the remainder theorem? What would the remainder theorem tell us? Well, let's look at that. Eraser here. The remainder theorem says that the error term, so if we would write the remainder theorem says the cosine, well, we'll stay with the red, why not, is equal to P4 of x, that's our approximation, plus the remainder at 4 as a function of x. And we might call this, let's get back to black, let me say. Get back to black. We would call that the error term. Error as a function of x. And the remainder theorem says that, for instance, in this case, R4 of x is going to be equal to, well, it's going to be it's going to be the first skip derivative. Remember, the zero term is 0 because cosine's an even function. So then the first skip term is really the x to the 6th term. So it's going to be the 6th derivative evaluated this magical c times x to the 6th over 6 factorial. Well, we don't know what c is, and we'll never find c, but we do know c is between the center point and the x, where you're going to evaluate the error. Okay? So what is this? What is this thing here? Well, the 6th derivative of this, remember if you go, the first it would be minus sine, minus cosine, sine, cosine. So the 4th derivative comes back to cosine. The 5th derivative is minus sine. The 6th derivative is minus cosine. And it's not going to really matter, but if you really wanted to find the 6th derivative, that would be minus cosine of c. And remember, we're not going to find c. We're not going to find exactly what the error is, but we're going to say the cosine of c in this range is always less than or equal to 1. Right? We're going to pick c equal to 0 and say that's equal to 1. So we're now going to say R4, the remainder theorem, which is equal to the error of x. And by the way, let's talk about the absolute value of the error. The absolute value of the error is going to be, that's equal to this minus cosine of c x to the 6th over 6 factorial. But we don't know what that is, but we know it's less than what? It's less than x to the 6th over 6 factorial. Now, what do I want my error to be? So let's review this. I want my error. What did my question ask for? Well, my question wanted the error to be less than 0.001. Is that right? 0.002. So the error, the true error, is going to be less than x to the 6th over 6 factorial, x to the 6th. And I want that to be less than 0.002. So if I find x such that it's less than 0.002, I can guarantee here that the error then is going to be less than that. So if I go ahead and solve this, I would say what? X, well, x, and again, work on the positive side of this. X is equal to what? It looks like it's 0.002 times 6 factorial, and I'm going to take the 6th root of that. And when I do that, what am I going to find? It looks like I'm going to find that's going to be equal to 1.0.063. Yeah, that's hard to see. 1.063. Does that make sense? Does that make sense compared to my calculator? So I got answers from this case, and let me just review the answers we just got. Okay, so okay, now my calculator it said x would be less than 1.066, greater than minus 1.066. Remember, it's even. And the remainder theorem sometimes called the Lagrange remainder theorem, told me as an x would be between minus 0.063 less than 1.063. You see the difference between these two guys? Does that make sense? Does it make sense that the remainder theorem that gives an upper bound would actually have an interval inside the true interval? You need to convince yourself that is correct. That is correct. This interval needs to be smaller than that one. Up here, this is the true error. Here, we used an upper bound. Upper bound approximation. Okay, we will be back then to answer part B to this question, where we look at how can we change the problem when we want to find the order required to have a good enough approximation. See you soon.